Alrighty, guys. Good evening. At least for me, anyway. It's evening. And welcome back to Algebra 2 today. As you can see, I'm out for the day. So you'll have a sub in here, and they should have gotten you navigated to our video lesson for today. The good news is that today's lesson is pretty straightforward. We're essentially just kind of discussing how to work with logarithms. In terms in particular, we're trying to figure out how to evaluate these things. So if I give you a logarithmic expression, you'll be able to tell me exactly what the output of that is. And that's going to kind of dovetail into some skills that we need later to really start talking about how to revisit exponential equations and solve them through the use of logarithms. So again, pretty straightforward lesson today. Shouldn't be too terribly long. As you guys settle in for the day and you get started with the video lesson, be sure that you're turning in your cell phones to the correct slots at the wooden caddy. The sub has instructions to collect phones from you guys, so should make sure that you turn this into the correct assigned slot so the sub knows exactly who's there and who's following along with the policy. Apart from that, though, as we get rolling into our time for today, what I want you to do is grab your old classwork assignment for practice 7.1. And I want you to find this first problem here where we're trying to graph a logarithmic function. What you'll notice about this guy is not only is it a logarithm, in this case, the log base 2, we have three transformations present. We got that negative out in front, we got the -5 in the argument, and we got that +2 there on the end. We're trying to graph that thing totally by hand without using a graphing calculator to do it. And that's kind of a tall order here, especially for a warm up on something that we just picked up in the last lesson. What I want you to do real quickly with your group mates is start just by identifying what you think these three transformations are going to do to the original graph to get this guy. Once you've discussed what you believe those transformations are, here's what I want you to think about. If you were to temporarily ignore those transformations and just focus on getting the graph of the log base 2 of x first, what are the coordinates you're going to need in order to get that graph drawn? And think about how that's going to connect back to, say, the exponential expression that this is going to be the inverse of. So I'll kind of leave it up to you guys here for a few minutes. I want you to pause the video, maybe with your partner next to you, with a friend nearby. I want you to think about how you're going to take away those transformations to get to this parent. But then if you're trying to graph the parent, how does this connect back to the exponential version of this that we saw back in 7.1 and that we're playing a lot with in Unit 6? Let's take a moment there. All right. So we got a logarithm. We're trying to graph this guy, and it's a bit of a tall order. We're trying to figure out exactly what on earth the graph of a logarithm even looks like again, just to kind of refer back to what we saw in the first lesson. And then we're going to slowly sort of work these transformations back into play. If I take a look at this function for f of x, I'm going to notice that I have three transformations present. I see this +2 over here on the end. What that's going to tell me, according to our transformation template, is that this graph's going to go up 2 units, just like every other family of functions that we've seen. If I take a look at this -5 on the argument inside the parentheses there, just like every other function, I know that that actually means that it's going right 5 units. And then I've finally got this negative out in front. And in the past, we've seen that this a term can do two things. It's both a vertical stretch or compression, depending on the value that's out there. Or if it's a negative, it's an over the x-axis reflection. So it's turning the whole graph upside down. So all I'm really doing is just kind of making a mental note of these three things so that once I have the graph of the log base 2 of x alone, I can just follow the directions of the transformation to get the new graph totally by hand. Now, the question still remains, how on earth are we supposed to get the coordinates for something like the log base 2 of x, right? Once we have some coordinates, we'll be able to graph this thing, but it's kind of tricky to think about what the right coordinates will be. So one way that I like to think about these guys, and this goes back to what we saw back in lesson 7.1, is that a logarithm is essentially a fancy way of saying what power do you have to give the base to get to this end result in the parentheses. So if I've got the log base 2 of x, and I'm trying to think about graphing that, something that might be a little easier to approach is the original exponential expression 2 to the x. Notice that I chose the same base for the exponentiation as the base that I have for the logarithm. And all I'm really going to do from there is just sort of think about some coordinates on this and how I'm going to connect that back to the logarithm, since I know these things are really inverses. They're opposite sides of the same coin. So in this particular instance, I might start nice and easy. If I do 2 to the first, I know that's just a 2 by itself. I know 2 to the second is a fancy way of saying 2 times 2. And I know 2 to the third in the same boat there is like 2 times 2 times 2. So I get 2, 4, and 8 for those outputs. Now, if you ever forget the zero power property or the negative power properties, just think about the sequence here going backwards. As the sequence increases going down the table, you're doubling your values. As you go backwards in the table, you're dividing by 2. So if I wanted to remember what exactly 2 to the 0 is going to be, or in fact any other base to the 0, this process of working backwards and dividing by that common ratio is always going to lead me back to the notion that something to the 0 is equal to 1. If I continue going backwards and dividing by 2, I'm going to see that I get a half and then a fourth. So 2 to the negative 1 is like 1 over 2 to the first. 2 to the negative 2 is like 1 over 2 to the second, and that's where I get that 1 over 4. So now I've got some nice coordinates, right? What we saw in the last lesson, though, is that since logarithms and exponentials are inverses of one another, they're two sides of the same coin, that means I can take the domain and the range and switch them. And if you're thinking about domain and the range in terms of just coordinate pairs, domain's the x and range is the y. So if you ever get stuck on graphing a logarithm, find the exponential and just switch your coordinates. And you get the logarithm out of that pretty darn fast. So for example, in the exponential, I had the coordinate negative 2 comma 1/4. In the logarithm, that's going to be 1/4 comma negative 2. In the exponential, I had negative 1 comma a half. For my logarithm, that's going to be a half comma negative 1. So all I'm doing is just taking those coordinates and flipping them around. So at the end of the day, I can get these coordinates out of it, and that's going to tell me what the original logarithm looked like, and then I can apply the transformations. So just sort of jotting these down, I have this initial coordinate at 1 comma 0. You'll notice that almost for all logarithms, this is like the initial value. Instead of on the y-axis, this guy's on the x-axis, compared to what we saw for exponentials. Then I've got, say, 2 comma 1. I've got 4 comma 2. And then it jumps all the way out to 8 comma 3. And then if I look at some of my early values in that table, I've got a half comma negative 1 and a fourth comma negative 2. What you'll notice here for this logarithm is that it's slowly going up and to the right. It's going down incredibly fast, but it's not quite clearing that y-axis. You can give negative powers on base 2 and get ridiculously small numbers. So if you switch those things, ridiculously small inputs on a logarithm give really large negative values, so it goes down quickly in that direction. Now, once I've got these coordinates, really all I'm doing to get my final graph for this original function f of x is just following the directions. I need to go up 2, I need to go right 5, and I need to flip it to be upside down. My advice is to do the reflection first. It's a little tricky to think about what reflecting over the x-axis is later when all of a sudden you've shifted things up or down, and you got to remind yourself that the x-axis travels with that. So to kind of short circuit that weird conundrum later, I reflect all of my coordinate values first. So anything that I had, say, right side up in the original, I'm going to turn upside down in these y values, and that's going to be the reflection done. So if I got a coordinate at 4 comma 2, this guy's at 4 comma negative 2. I've got a coordinate at 8 comma 3, this guy's at 8 comma negative 3, right? And same thing with these kind of like fractional values there. I'm just taking the whole set of coordinates there and I'm just turning them completely upside down on their head. So that's the reflection done, and that's kind of the hardest one. The rest of these are going to be translations, right 5 and up 2. So every pair of coordinates that I've got, and I'll draw this in a different color, I'll draw this maybe in kind of this like purplish color, is going to be my final graph once I've transformed things. So I've got this coordinate at 1 comma 0. He's going to go right 5 to 6 and then up 2 comma 2. That's my final initial value for my graph. I have this coordinate at 2 comma negative 1. He's going to go right 5 to 7 and up 2 to be 7 comma positive 1. I've got another coordinate here at 4 comma negative 2. He's going to go right 5 to 9. He's going to go up 2, so that's now my x-intercept at 9 comma 0. I've also got these sort of like fractional values, right? So these guys are going to be kind of like right about here. And what I'm going to notice is that the original vertical asymptote, which was the y-axis, is also going to travel right 5 units. So it's kind of hard to see here, so I'll draw it a little offset from this sort of vertical coordinate line that I see here. So this guy is kind of like the imaginary vertical axis that this logarithm can't cross. So to sort of finish off the graph for this guy, all I'm really doing is just sort of connecting up my dots. And this sketch that I'm doing here in purple, that's my final answer for the graph of this function. Once I have the graph of that function, I can answer questions pretty easily about the domain, the range, and the end behavior here. If I'm thinking about domain, I'm just writing down the set of x values that this guy can take. I notice it goes right forever, but it only goes so far to the left. It can only go up to, but not including -5 in that leftmost direction. If I take a look at the range, it goes up forever. It also really slowly goes down forever. It goes more fast to the right than it goes down. But even though it's going slowly, it doesn't really matter. If you go forever, you'll eventually hit every y value in that negative direction. Then from there, I've got to do my end behavior analysis, right? These limits tend to throw people off. X approaches infinity or X approaches 5 is saying, hey, you're approaching a part of the graph from one side or the other. If X is approaching positive infinity, what that's trying to say is you're tracing the graph way to the right, and you're just telling us where the Y values are going. And we'll see in that case that it's going towards negative infinity. If you take a look at this other limit, though, this is kind of a rare occurrence. You see this a little bit with rational functions back in Unit 5. We'll see it here with logarithms. What this is saying is that you want to approach x equals 5 from the right-hand side, from the more positive x direction. So what I'm going to do here is just sort of trace the graph from the right side going left towards x equals 5, and I'm going to report what the y value is going towards. And in this case, I'll notice that as I trace from the right, this graph's going up to positive infinity. So a little extra analysis there on top of transformations. We talked about the logarithm being the inverse of the exponential. So we got the parent function, we transformed it, and then we did some analysis. There's one last example in the practice assignment that I want to kind of take a look at, and it's this guy. This function g of x equals the negative natural log of x squared minus 9. This problem's kind of tricky, and it's a bit of a curveball from out of left field. It's been a minute since we talked about finding the domain of a function algebraically. What we've talked about in the past with domain algebraically is we're essentially trying to figure out where a function breaks or goes undefined. We've seen with rational functions that you can't divide by 0, for example. We've seen with radical functions that you can't let the input be less than 0. You can't let it be negative if you're taking the square root, because then it goes imaginary. We're essentially thinking about the same thing here, in the sense that when we're looking at a logarithm, we're kind of answering the question to ourselves like, okay, what are the types of things that we can take a logarithm of? Now, if you take away the fact that there's that quadratic term, that x squared minus 9 in the logarithm, and you take away that over the x-axis reflection out in front, this is essentially just a natural logarithm. If you think about any logarithm, including the natural logarithm, which is just the log base e, we can take the natural logarithm or any logarithm of a positive number, but we can't take the logarithm of nothing, and we can't take the logarithm of a negative number. And what we talked about in 7.1 is the reason behind that is that you can take a base and give it a power to be multiples of itself. You can give a base and a power to equal some really crazy choices of values, but you can't give something a power to be nothing. You can get it close to nothing, but not nothing. You get these crazy fractions, but not 0. And if you can't get to 0, then you definitely can't become negative. So when we talk about logarithms, the domain is always greater than 0. Now, once you kind of go back to the original problem here, where it's not just the natural log of x, it's the negative natural log of x squared minus 9, we want to think about really where the problem is. A logarithm can handle anything so long as the input, the thing inside the parentheses, is not negative. It's got to be greater than 0, right? So if that's true, then that means x squared minus 9 itself must be greater than 0. It can't be equal to 0 and it can't be negative, otherwise we can't take the logarithm of this, no matter what it is. So to help us kind of figure out the domain of this function, what I want you to think about is if you look at this quadratic, which went down 9 units in terms of its y-intercept, we're essentially answering the question on this graph where this thing is greater than 0, which is to say that it's above the x-axis. Now, what I'm going to notice is that if I'm looking for where this thing is above the x-axis, that's kind of like the same question of saying, hey, where's x squared greater than 9? So I can kind of take a more algebraic approach here, where I'm just sort of solving for x, but I've got the plus minus root 9 thing going on. If I'm thinking about it graphically, what I'm going to notice is that I have to be left of x equals negative 3 and right of x equals positive 3. So long as I'm left or right of those x values, the graph is above the x-axis and it's a positive number, which means I can take the logarithm of it and not have a problem. So this is kind of a more challenging problem. This goes back to a skill that we've seen a couple of times in a couple other units in semester 2 that we may have not practiced for a while. So I just wanted to make sure this didn't come out of left field and surprise anybody. It's a nice little problem just to kind of get the gears turning. So 7.1, we've introduced what a logarithm is. We talked about this inverse relationship between exponentials and logarithms. We started working with graphs and transformations. We're going to continue to get a little practice with that as we go through some of the materials further along in the unit. But really where we want to go with this is show how that you apply logarithms to solve exponential equations that we couldn't do by hand back in Unit 6. There's a reason we still use logarithms, and that's predominantly what it is. We're going to have a content check for you guys, our B-Day crew, on Monday, the 28th of April. It's going to be on both 7.1 and 7.2. If you're missing the Unit 6 summative, or you have components of that summative that need to be completed, those are due by Friday, May the 2nd. Beyond that, we're going to be about halfway through Unit 7. We're going to be preparing to take a capstone and get ready for the final exam, so you need to have it done by that date. Otherwise, when a capstone does come up, we're going to talk a little bit about exponentials and logarithms on that guy. It's about a 50-50 split. If you're passing 2 of the 3 capstones so far, you're in good shape. You'll still take the logs capstone. You just don't necessarily need to fret about passing it. If you're passing only 1 of the capstones, you have to pass this one. If you're not passing any of them by this point, you definitely need to start finding some retake sessions to get those in the bag before people come find you your senior year. Otherwise, this is the next week or so at a glance. We've wrapped up with SAT testing with the Unit 6 summative out of the way. That's the last unit test of the semester. So really all we're really taking a look at are some content checks as mile markers. We'll hit that capstone to kind of get that in the bag, and then we'll worry about the final exam. So today in the notes, and I believe in the notes we're on pages 94 and 95 today, we are focusing on evaluating logarithms. So we've defined what they are. We've kind of explored some initial properties and how they connect back to exponentials. Today we're really emphasizing how you work with them in calculations. So what we know so far is that a logarithm is best defined as some mysterious thing that's essentially answering the question, what power do I need to give this base to get a desired result? So for example, in a logarithm, if y inside parentheses there is the result and b is your base, x is the correct choice of power to go from b to y. So for example, if I was taking the log base 2 of 8, I know my answer would be 3 because 2 to the third is equal to 8. So this slide is just kind of highlighting different ways to think about that logarithm, kind of converting back and forth to that exponential format. It's a really powerful framework for understanding what it is we're trying to do with evaluating. The other thing that we explored, especially with log base 2 and 2 to the x, is that when you graph these on the same coordinate grid, you get these sort of inverse graphs. They're complete opposites of each other. They have that nice diagonal axis of symmetry. The other thing you'll notice is that if they're inverses, the domains and the ranges are flipped. The y-intercept becomes the x-intercept. The horizontal asymptote becomes the vertical asymptote. Everything about it is its total opposite. So if you ever need to graph a logarithm and you get stuck, try getting the exponential and then just inverting your coordinates, and from there you're good to go. So where we are in the notes is section 7.2. I think that's page 94 or 95. And again, what we're really focusing on here is evaluation. We're trying to do calculations with logarithms. What you'll notice for a lot of these guys is that the template that they're written in is going to be f of x is this, or g of x is that. Find f of 8, or g of 81, or f of 1. So all we're doing is plugging in the x, and we're trying to simplify down the expression. We're evaluating. Given an input, what's the output? If I want the answer, say, to the question f of 4, when I know f of x is the log base 2, all I'm really saying is, hey, what's the log base 2 of 4? Now, remember that a logarithm is just a funny way of saying what power do I need to give a base to get to this desired result. So if I think about the associated exponential statement here, 2 to the what is equal to 4, I know my answer is 2 because 2 squares 4. And that's really it. That's all we're trying to do here. If I'm taking a look at, say, f of 8, where I've got the log base 2 of 8, what I'm really trying to say there is 2 to the what is equal to 8. And in that case, it's 3. 2 by 2 by 2 is 8. If I'm looking at something like f of 1/2, this one's a little more interesting in the sense that if I want to make a 2 look like 1 over 2, I've got to give it a power to get there. And this kind of goes back to our exponent properties, where if you want the value to be the same, you just want it to be upside down, it means you need a negative exponent in order to accomplish that. Given that it's a 2 in that denominator instead of a 4, an 8, or a 16, I know it's like 1 over 2 to the first, which is the same thing as 1 over 2. Maybe another interesting one is the log base 2 of 1, which is essentially a funny way of saying 2 to the what equals 1. And there's only one thing that we know that does that. That's the 0 power. So you'll notice that you need exponent properties to evaluate logarithms. You're going to have to remember the 0 power property, the first power property, your negative power properties, and in some of these, you'll even need to know that radical power property or the rational exponent property. So we'll kind of play with these as we go. We'll get more practice and get more comfortable with it. There's a couple of these down here that are going to be kind of interesting questions. In these two, they ask us to evaluate the log of -1 and the log of 0. And essentially what that's saying is, hey, what power do you give a 2 to look like a negative? Or what power do you give a 2 to look like nothing? But here's the thing. If you think about, say, an exponent table for 2 to the x, I can build out a lot of these values pretty quick and investigate what's going on for some different choices to see if I can arrive at an answer to that question. What I'll notice is that if I choose positive integer powers, 2 to that power is going to be some increasing value. It's going to get larger and larger and larger, which is not -1, and it's not 0. If I do 2 to the 0 power, it's not -1 or 0, it's 1. And if I think about some of my negative power properties, I don't get a 0 and I don't get a negative value. I just get really tiny positive numbers that are not nothing. So sometimes you'll be asked to evaluate a logarithm where you can't find the power that takes the base and makes it look like the argument. If you take a look at the graph of a logarithm before we transform it, you'll notice that these are things on the other side, the left-hand side of that vertical asymptote. There's no way to get there. You can't take a log of these values because there's no power that takes a base and makes it look like them. So we say these are just undefined values. On occasion, you'll run into those. And in those instances, there's not really an answer, so we say undefined. Over here on the right-hand side, we're thinking about a logarithm just by a different base, kind of a new base for us. In this case, it's base 9. If you're talking about the logarithm base 9, and say you want to evaluate at 9, you're still answering the same question. What's the power you need to give this base to equal this argument? And in this first logarithm, we'll see that this still evaluates to a 1. If I've got the log base 9 of 81, I'm essentially answering the question, 9 to the what equals 81. And I'll see that that power is 2. Now, if I see that I'm evaluating the log base 9 of 1 over 81, I know 81 is 9 to the second, but to get it to look upside down like that, I need a negative power. So if I combine those two things together, I'll see that that logarithm is -2. Now, these next few ones get kind of interesting. If I'm looking at g of -3, essentially what I'm saying is, hey, how do I get a 9 to look like a -3? Again, there's no power that you can give 9 to look like a negative number. You can do 9 to a larger and larger and larger positive power, which in case it's going to go really big really quickly. You can give 9 a 0 power to be 1, and you can give 9 negative integer powers to be really, really, really tiny values, but they're always something, not nothing. And if they're not nothing, then they definitely can't be negative. So this is, again, an undefined value. You can't take the logarithm of a negative argument. There is no such power that takes something and makes it look like nothing or a negative value. So it's always good to kind of keep an eye out for those. These next two get a little more interesting. If I'm taking a look at g of 1/3, what I'm saying here is that I want to take a 9 and I want to make it look like a 1/3. This one's best handled in 2 steps. One thing to think about is if you take a 9 and you're giving it a power to look like a 3, what can you do to a 9 to get a 3 if you're not thinking in terms of exponents? You can divide by 3. That definitely works. But another way to think about it is instead you're taking the square root of 9 to get 3. Now, if you think of it that way, we know that the square root of 9 is the same thing as 9 to the 1/2 power, based off that rational exponent property. So if I want to get a 9 to look like a 3, I know that I have to use a power of a half. But if I want it to not be a 3 but a 1/3, I know I need a negative exponent. So if I combine those two things together, ultimately what I'm going to see here is that my answer is the -1/2 power. So this one kind of freaks people out on 2 fronts, right? Not only is there that negative power property, you're also combining it with the rational exponent property. So we're thinking in terms of radicals becoming fractional powers, and then we're putting these two things together. It's kind of tricky to think about there, right? But it does work. Now, this last one is kind of going to go in the same direction. I've got the log base 9 of 27. I can't give 9 a power to look like 27. 9 to the first is 9, 9 to the second is 81, 27 somewhere in between, right? What I can do is instead of thinking about 9, think about 3. Since I know that 9 to the 1/2 is equal to 3, I'm going to sort of hold on to this fact. And if I think about 3 to some power equaling 27, I'm going to see that that's like 3 to the 3rd power. So if I combine these two facts together, that 9 to the 1/2 equals 3, and 3 to the 3rd equals 27, I'm essentially doing 9 to the 1/2 to the 3rd power. And that's the power to a power property, which means I'm multiplying those two exponents together. So again, this is kind of a combination of two things at once. 9 to the 1/2 is 3, 3 to the 3rd is 27. Repeated powers exponentiating each other means I multiply. So my exponent in this case is the 3/2 power, or the 1.5 power. Now again, think of it this way, right? 9 to the first is 9, 9 to the second is 81, so it should be something between 1 and 2. This is in the ballpark. So evaluating these logarithms sometimes makes us think about these exponent properties and how we're going to get familiar with them in a few new sort of complicated contexts. So we have to get comfortable with those exponent properties if we want to evaluate logarithms successfully. Now, there's a few more examples here in the notes that I want to touch on, just to continue to reinforce something that we recognized in 7.1 that's going to be really important going into the rest of the unit. If you take a look at these expressions in the notes, they're asking us to evaluate, which is essentially saying to simplify these things down. But they want us to evaluate these kind of complicated expressions. They want us to evaluate 2 to the power of the log base 2 of 5. they want us to do the log of 10 to the fifth, and then down below it gets even worse, right? There's these algebraic expressions flying around. For this one, I find that it's easier to take each of these calculations one small step at a time. And what I mean by that is if you're focusing, say, on 2 to the power of log base 2 of 5, let's figure out first what the log base 2 of 5 is, so that we can then raise 2 to that power and see what we get first. Now, what you'll notice here is that if you're doing the log base 2 of 5, you're trying to answer the question, 2 to the what is 5? That's not an obvious answer, right? 2 to the first is 2, 2 to the second is 4, and 2 to the third is 8. But 5 is somewhere between 4 and 8, so this power must be somewhere between 2 and 3, but I don't know what it is. What I want you to do is grab a graphing calculator. If you have your own, you're welcome to use it. If you don't have your own, I want you to grab one from the back wall there, and I want you to follow along in this process. You can evaluate all sorts of different logarithms on a calculator. The old ones that you're borrowing from the back wall, you have to be careful because not all of them are able to do this sort of calculation, which is why we recommend at the beginning of the year you buy your own and you buy a TI-83 or TI-84. Those guys usually can handle this, but some of those older calculators can't. What we want to do is take a logarithm. And what you'll notice on the calculator is that there's two of these guys. There's the common log here, and there's the natural log. Neither one of those are the log base 2. To get the log base 2 of something, you're going to have to hit the math button, and you're going to have to scroll down in this list until you see log base. Most of the calculators on the back wall are going to be able to do this, but not all of them. If you grab a calculator that can't do this, you should try and trade it out for one that can. But we've only got so many to spare. Now, what we're trying to do here is take the log base 2 of 5. So if you enter that into the calculator, you're going to get a really crazy exponent. You're going to get something like 2 to the 2.321928095 power. It's irrational. It keeps going forever. It's a crazy decimal power, but it works. If you do 2 to that power, what you'll get in this particular instance is 5. So there is a power that makes it work. It's just not an obvious choice. You need a calculator to help you sort of pin down what it is. Now, going back to our problem, right? We know the log base 2 of 5 is this crazy decimal. I want to do 2 to that power and see what I get. And what you'll notice here is when I plug that all in, I get right back to where I started here. I'm right back to equaling 5. So if I've got that base of the exponentiation being the same thing as the base of the logarithm, they sort of cancel each other out and they just leave behind the argument 5. That's a really important thing that we want to track so that we can apply it later as we get further in the notes. Now, let's try maybe the log of 10 to the 5th. This one can actually be done by hand, but you can also plug this into the calculator to kind of verify it as you go along. For this guy, what I'm trying to answer is what base raised to a power is going to look like 10 to the 5th. If you're dealing with a logarithm in which they don't specify the base to you, you can always assume that that's base 10. We call that the common logarithm. It's so common, it's so frequently coming up in math that people kind of drop the base 10 because it's just assumed, given that everything else in our number system is also base 10. So don't let it fool you. This is really a fancy way of saying, hey, 10 to the what equals 10 to the 5th. And when you pose the question that way, you'll notice that the power must equal 5. But if you take a look at that logarithm, the base of the log and the base of the exponentiation are the same exact thing. So it's kind of like they're canceling each other out, and it's just that power that's important. So if we recognize that in these first two examples, it's going to allow us to take that notion and apply it when we're dealing with these more unfamiliar contexts. If I've got 7 raised to the power of the log base 7 of x to the second, I don't know what x to the second is. It's just some mathematical expression. But that 7 raised to the power of log base 7, those are total opposites. They're going to cancel each other out. So even though I don't know what x squared is, because I don't know what x is, I know that the only thing left over here when I simplify is just x to the second. That's all that's left. Same thing down here for this logarithmic expression. If I've got the log base 4 of 4 to the x plus 1, well, what I'm really saying here is 4 to the what equals 4 to the x plus 1. And that must mean that my power is just x plus 1, right? It's like they're canceling each other out completely. Again, that is a really important fact that's going to serve as a really important stepping stone later on in the unit when we try and solve exponential equations by utilizing logarithms. What we saw back in 7.1 is that these guys are polar opposites, right? They do the exact opposite of what the other one does. So what that means mathematically is if you have an exponential expression that you take the logarithm of, or you have a logarithmic expression that you exponentiate, these things are going to completely cancel each other out. And you're just going to get whatever the argument of the log is or the power of the exponentiation is. So it just leaves behind a simpler term. It's like multiplying something that was dividing. It's like adding something that was subtracting. They just cancel each other out in this context. So this is a crucial property of logarithms and exponents. If you want to undo an exponential expression, use a log. If you want to undo a log expression, you exponentiate. They're really total opposites. They're two sides of the same coin. So doing one and then the other is just going to leave you full circle. What I want you to do real quick with your group mates, just to solidify the thinking, is take like maybe 5 minutes to try some of these calculations with your group mates. You'll find these in the notes in section 7.2. I believe it's like page 94, page 95 there in the notes spiral. I want you just to try your hand at doing some evaluations. We've really focused on doing these things by hand. Don't be afraid to use the calculator now that you've seen how to get that log base function, just to check your work as you're going, just to make sure you're on the right track. Again, pause the video, take like maybe 4 to 5 minutes with your group mates just to try a few of these, just to get comfortable with that inverse relationship and what a logarithm is really asking us to accomplish here. All right. So I'll start maybe on the left-hand side, just to kind of reinforce calculations with logarithms, just to continue to get comfortable with answering the question of what a logarithm really is. What I've got on the left-hand side are two functions, g of x and f of x. G of x is some kind of logarithmic equation where it's 4 minus the log of x. F of x is just a linear function, x minus 8. If I see g of 1 or g of 100 or g of root 10 or g of 1 over 1,000, I'm plugging those x's into x in that g function, and I'm just simplifying it down to see what I get. So for example, if I've got g of 1, this is essentially saying, hey, do 4 minus the log of 1. Remember that if I don't specify the base on that logarithm, it's base 10. So if I'm trying to simplify this down and I think about that logarithm and I want a 10 to look like a 1, what power do I give 10 to be 1? That power is 0, right? So if I take a look at this initial equation, I'm essentially doing 4 minus 0, which means that my answer there is just 4. If I take a look at g of 100, I'm doing 4 minus log of 100. If I'm focusing on that log component and I do the log base 10 of 100, I'm essentially saying what power do I give a 10 to look like 100? And that power is 2. So this is the same thing as doing 4 minus 2, which is just the answer 2. And I'm good to go. So you'll notice a lot of the times with these problems, we're just kind of plugging things in and trying to simplify it down. We're condensing, right? We're essentially just seeing the output for a given input. Now, g of root 10 is a little more interesting. if I do 4 minus the log of root 10, I'm going to focus on that log component first and then put it back together at the end of the day. What power do you have to give a 10 to make it look like you're taking a square root of it? That comes back to the rational exponent property, right? Where I'm doing the 1/2 power to make it look like the square root of 10 to the first. And if that's kind of funny, go look at the poster in the top left corner of the room there to check out that property where it's a to the m over n is the nth root of a to the m. It's the same thing here, it's just a little more simple. So in this context, I'm doing 4 minus 1/2, and that's equal to 3.5. If I've got g of 1 over 1,000, I'm essentially asking the question, hey, 10 to the what is not just 1,000, but 1 over 1,000. So to get 10 to look like 1,000, I'm going to have to do 10 times 10, which is 100, and then 100 times 10, which is 1,000. So I got to do 10 to the third. However, if it's a fraction that's upside down, it's not just a power of 3 that I need, it's a power of -3. So this is the same thing as 4 minus 3, which is equal to 1. Now, these last two examples get a little more colorful. These guys are examples of something that we learned back in Unit 2 a long time ago in October that we saw a little bit of along the line kind of in the end of Units, I think 4 or 5. This is something called function composition. Function composition is essentially the idea that you're going to take the result of plugging x into one function which is going to give you some kind of output, right? But then you're going to take that guy and plug it into another function and see what that result is. So it's kind of like you're daisy chaining the outputs of the functions together. Now, the order of the composition definitely matters. G of f of 108 is going to give you a very different answer than f of g of 108. My advice is to start in the inside of the composition first, and then work your way out in the layers to get your final answer. So what I need to do first is figure out what f of 108 is. And f of x is this nice, easy linear function. So I do 108 minus 8, and I get an answer of 100. So really what this is trying to tell me to do is say, hey, what's g of 100? And that's the same thing as 4 minus the log of 100. So that's really the same thing as 4 minus 2, which is just 2. So I'm taking it one small step at a time when I do composition. I'm starting in the inner layer, and I'm going out a layer. Now, let's say that I wanted to tackle, say, f of g of 10. What I probably want to do here is figure out what g of 10 is first, and then plug that result into the function f. If I think of g of 10, I'm doing 4 minus the log of 10. The log of 10 is just 1, though. 10 to the first is 10. So this is the same thing as 4 minus 1, which is equal to 3. So now what I'm going to do is f of 3. And what I see there is that that's 3 minus 8, so my final answer for that guy is just 5. So it's just a little practice with some of the calculations there. And again, you can verify this with the graphing calculator just to sort of double check your work along the way. On the right-hand side, we're focusing on that notion of inverse operations, right? If I do 3 to the power of log base 3 of 7, the fact that the base of that exponentiation is matching the base of the logarithm means they're going to cancel each other out and just leave behind that 7 in the arguments place. If I take the natural log of e to the x, remember that the natural log is the log base e. It's just kind of a shorthand so that we don't have to write 4 letters to get that logarithm expressed. We can get it down to 2. So if I'm doing the log base e of e to the x, then the base e in the exponentiation is going to cancel with the log base e, and it's just going to leave behind that power. That's it. They just canceled each other out to leave behind that last term there. Same thing with 10 to the log base 10 of x plus 1. If I don't specify the base of the log, I can assume it's base 10. So because those bases match, it's just the argument of the logarithm that's left behind. This last guy's a little different. You can approach this guy 2 different ways. You can say that this is the question 5 to the what equals 25. And in that case, you'll figure out pretty quickly that power's 2. A different way to look at it is to say, hey, I'm doing the log base 5 of 5 to the second in parentheses. And since the base of that logarithm is matching the base of the exponent, the only thing that gets left behind is the power of 2, but you get the same answer either way. So just a little extra practice, primarily with working those calculations, but also continuing to reinforce that notion, right? That logarithms and exponentials are total opposites of one another. They're two sides of the same coin. For your homework today, I'm trying something a little bit new in the sense that instead of a printed hard copy, we're going to do a digital practice assignment. The assignment that I'm going to give you can be found on Schoology. If you go to our Schoology page, in that lesson 7.2 folder, you'll find a hyperlink here for 7.2 homework evaluating logs puzzle. In order to complete your homework assignment, you're going to have to make a copy of this in your own Google Drive. When you make a copy of this, on slide 2, you'll notice that there's this sort of template on the right-hand side, this pyramid-looking shape, and a bunch of little triangles on the right-hand side. The goal of this is to take the first triangle that has a 1 in the center of it, which means you're going to drag that and put it into the pyramid on the right-hand side where you see that 1, is to try and match up the sides of the triangles that are really the same exact thing. So what you'll notice as you take a look at some of those different triangles in there is that you might have logarithmic or exponential statements. You might even be solving some equations. But you'll know you're on the right track when two sides of two different triangles are really the same exact thing. So they're going to be side by side there. And you're just kind of trying to drag and drop these until you figure out where all the pieces of the puzzle go. So it's a nice little digital activity. It's pretty interactive, lots of drag and drop. When you're done with the puzzle, when you've got it fully assembled and you think your answers are correct, in order to submit, you're going to have to go File, Download as a PDF. And then you're going to be able to submit that to Schoology, and that's going to be your homework for 7.2. You're welcome to work with partners on this one. Just make sure that every student, just like usual, submits their own copy of the assignment. In particular, you want to submit this one on Schoology because there's no hard copies for it. If you have any questions on getting started with that puzzle, if anything's feeling kind of wonky in that process, definitely let me know when we come back on Friday. I'll be more than happy to help answer questions then. Apart from that, though, that is going to be the final item of business for today. We sort of reinforced the notion that exponentials and logs are inverses. We got some extra practice of answering that question, what power do I raise a base to get a result, which is really what a logarithm is. And we got a little bit of an extension there, right, to kind of take it some further steps along the way to do calculations, either by hand or by plugging some things in the calculator. So when we come back on Friday, we'll hit our content check and see how it's going. We'll have a little bit of work time just to kind of check in and answer any last minute questions. But apart from that, I think that's a nice place to stop. Any time that we have left in class for today is work time. So you should be working on finishing classwork 7.1 or classwork 7.2. Otherwise, I hope you guys have a great rest of your day. I'll see you guys again on Friday.